Now we will look at sound waves in more detail. This is a slinky, a spring, and this is at rest. When I move this slinky in the direction parallel to the length of the slinky, then I produce longitudinal waves in this slinky, as previously stated in this video. These places are called compressions, and these places are called rarefactions. Compression. Okay. Now, just like the slinky, when I move it like this, there are compressions and rarefactions, and this is air. If I could move the air like this, just like the slinky, the air can also develop such compressions and rarefactions. These are the compressions, and these are the rarefactions. In the spring, in compression, the turns come closer to one another, and in the air, in compression, the air molecules come closer to one another. So, in this way, sound is transmitted in the air. In slinky, I use my hands to produce the longitudinal waves, and in air, our vocal cord and the speakers, they push the air like this to produce these sound waves. Okay, so the molecules in air, they were supposed to be like this, equally spaced. But when there is a sound box or a vocal cord, the air molecules move from one place to another. They don't get transferred from one place to another. When you talk, the air from your mouth doesn't travel from here to another place. The air just stays here and it just vibrates for a short period of time while you talk. When you stop talking, the air molecules also stops moving. When you start talking again, the air molecule then starts oscillating again, but it remains in this position. It doesn't get away from this position. Let us look at a bit more detail what happens to that air molecule. So imagine that this is an air molecule. So this is moving in this position. This is vibrating like this. Okay. So for this air molecule, this distance, the maximum distance that it moves from its equilibrium position, this is equilibrium position, the position that it occupies when there is no sound. The maximum distance that it moves from its equilibrium position, that is called the amplitude of sound. And this amplitude defines the loudness. The louder we talk, the further the air molecule moves from its equilibrium position, and the louder our sound sounds, our voice sounds. And pitch of the sound depends on its frequency, how fast the molecule is moving. If the molecule is moving slow, then our pitch is low, and if the molecule is moving very fast, our pitch is high. Okay, so the pitch of the sound, that is dependent on the frequency of the sound, the frequency of the air molecule, and the loudness, that is dependent on the amplitude. Just like light waves, sound waves also undergo reflections, and this reflection of sound wave has a very special name. That name is called echo. So like all other waves, sound waves have their frequencies: 2 Hz, 20 Hz, 2000 Hz, 20,000 Hz, and we humans can only hear certain frequencies of sound. The human audible range is 20 Hz to 20,000 Hz or 20 kilohertz. This is the human audible range. Sound that has frequency lower than 20 Hz, those are called infrasound. And sound that has a frequency higher than 20,000, those are called ultrasound. Infrasounds are used by dolphins to communicate, and ultrasounds are used by bats to communicate, and also in ultrasonography. Now we are going to look at a very fun experiment to measure or calculate the speed of sound. That's you, that's your friend. Your friend pulls the trigger on a gun. Okay? The distance between you two is 100 meters. From the moment that you see your friend pulling the trigger and you hearing the sound, 0.303 seconds. Just for example, but this is an actual real life value, by the way. Okay? So from the moment that you see your friend pulling the trigger, you turn on the stopwatch, and when you hear the sound, you turn off the stopwatch. So that is the time taken for the sound to come from here to here, right? Okay, that's 0.303 seconds. The distance is 100. We know that distance is equal to speed into time. So we know the distance, that is 100. We don't know the speed, and we know the time, that is 0.303 seconds. So our speed turns out to be 330 meters per second. This is actually the speed of sound in air. Okay, what if you don't have a gun? What if you don't have 100 meters of space? And what if you don't have a very good friend who can help you in this boring experiment? Then you can use an electronic version of this experiment. Okay? Here you have a source of sound. This sound could be anything. Could be a song, could be anything, could be a click. Okay? This is your sound, and these are two microphones. They are placed 1 meter apart. 1 meter is about this much, a little bigger than this keyboard. These are 1 meter apart, and this is an electronic device. This sound hits this microphone, and then it travels and hits this microphone again, this sound. Okay? This distance is 1 meters, and when this sound hits this microphone, the timer starts, and when this sound comes and hits this microphone, the timer stops. The time taken for the sound to hit this microphone after hitting this microphone, that is the time taken to travel from here to here, is displayed by the machine as 0.003 seconds. Once again, using the formula, distance is equal to speed into time. Our distance is 1 meter, speed we don't know, the time is 0.003 seconds. Our speed is there, 333 meters per second. This is also close to the speed of sound in air. So this is another version of an experiment that you can do to measure or calculate the speed of sound in air.